In this example, we're looking at the longitudinal motion of a rod. The boundary conditions are that it's fixed on the left side. There's a spring boundary condition on the right. We want to find the natural frequencies and mode shapes. The equation of motion for a homogeneous rod is EA, second derivative of longitudinal motion U with respect to x, is equal to the mass density cross-sectional area A times the second derivative of longitudinal motion with respect to time. Solution, a separable form. U will be spatial function U of x, t of t. Substituting into the equation of motion, we get EA U double prime of x, t of t. The right-hand side, rho A U of x, t double dot of t. And our usual thing here to separate out the x part, put those on the left side, we get U double prime divided by the u's is equal to, on the right-hand side, t double dots divided by the t's. What's on the left is a function of x. What's on the right is strictly a function of time. In order for those to be equal to each other, that must be a constant. We define that as omega squared. And so we get t double dot plus omega squared t is equal to a 0. And the u double prime plus rho over e omega squared, u is a 0. We will define this to be beta squared. So the response that we're looking for here, the spatial part, u of x is equal to a cosine beta x plus b sine beta x. So, just as we have in a number of examples up to this point, we need to enforce our boundary conditions in order to get whatever information that we can about beta and these coefficients of a and b. The first boundary condition is that on the left, the displacement is a 0, so u t of t, since that's equal to a 0, it says that u must be a 0. So again, that's equal to a. The second one, though, requires a bit more thought. What I'm going to do is I'm going to look at the right end of that rod, right here. The spring is attached there. So I'm going to take that attachment point and pull it away. So that attachment point is putting a force on the rod we know of EA du dx. The stress being E times the strain du dx, the force being EA. The equal and opposite force on that attachment point. There's also the spring. So this is, I should say, this is at x equal to L. The spring is there, and its force is going to be proportional to the displacement on the end. When U is positive, it means the right end of that bar is displaced to the right. The spring is compressed, so it pushes back like that. When I now sum my forces acting on that attachment point, which I'll just call that B, I have a minus EA du dx at L minus K ULT. And if we say that that attachment point has negligible mass, then that is a 0. So this is B here is what's happening there at x equal to L. So what we get from this equilibrium analysis is a boundary condition that says minus EA U prime at L, T of T, minus k u at L, t of t, is a 0. In other words, I have EA u prime plus k u is a 0. I think to be consistent here, I need to make this a big K. So let me change that, just so we're clear all the way through. This should be big K. Okay, so that is our second boundary condition. So what I will do is take what's left for u. The u prime is going to be equal to beta times b times cosine. Then I have k times sine beta L, and that is equal to a 0. We've got two things that multiply each other. Either this is a 0 or this one is. B equal to 0, check it out, gives you a trivial solution. So it is this one here which must be equal to a 0. So when I set that equal to a 0, and I solve for tan beta L, tan being sine over cosine, I get a minus EA over K times beta. And I'm going to rewrite the right-hand side that slightly differently. I want to get, since this argument of tan is beta times L, this non-dimensional number of that, I'm going to do the same thing on the right-hand side. I'm going to make this EA over KL times beta L. So this is our characteristic equation. It is different than the other characteristic equations we've run across so far in looking at the vibrations of the rod, the shafts, and the strings, in that there is no analytical solutions. No closed form solution for beta. So we will need to a numerical means and I chose to use a function in MATLAB for solving that characteristic equation. So what I've done here is I've chosen some value for alpha here. That's just a name. That's a ratio of EA, which is a stiffness-like term for the rod, divided by, EA over L, which is a stiffness-like term for the rod, as a ratio of that to K. So it gives you a measure of how stiff that the spring is compared with the rod. So how do we go about that? Well, what we're trying to do is find the place where tan of a function, let's say tan x, is equal to minus alpha x. We're trying to find the roots for x. In other words, where does tan function cross a linear function of x with a negative slope? Let's go and look at the next page or two of the notes. There should be a plot here. There we go. What's shown there in red is tan beta x. What's shown there in blue is minus alpha x. where x is equal to beta L. So we're looking for the roots of x, which in turn will obviously give us the roots for beta that we need. I also need to go up here and make a slight a correction here. This alpha is equal to EA or KL. I wrote it upside down. So for a given value of alpha, we define the slope of that blue line. And so this here is the first root for beta 1L, where these two cross is the second root for beta 2L and beta 3L. So the MATLAB routine we're going to use, we're going to have to give it a guess. And depending upon what that guess is, we will likely converge on either root 1, 2, or 3. And sort of the closer you are to 1, the more likely it is that you're going to end up with on root 1. But we run into some difficulties here. The difficulties are, as we move out into higher and higher roots, the slope of that function becomes more and more steep. Most functions you're going to, or most numerical means you're going to use to solve this are going to be based somewhat on a gradient or a slope of the function. So when the slope becomes nearly infinite at the root that you're trying to find, it's very easy for it to jump away from that root. So one way around that is, instead of writing it like this, what if we do it the other way? We move the tangent over on the right-hand side, make that a cotangent, move the beta L on the right side to make it 1 over beta L. And if we make a plot of that like this, again, now the red is the cotangent. The blue is the minus alpha beta L. So here, the roots we're trying to find, they're the same ones. That hasn't changed. But they are roots that are going to be where the slope is much better behaved. So I've always found in solving this kind of a problem to deal with this characteristic equation form rather than the other. They all end up being the same result in the end. It's just that the second one here just gives us a more manageable solution procedure. So what I did was I guessed, using that second case, I used the initial guesses there for odd multiples of pi over 2. And using the MATLAB routine called F0, these are the first 5 roots. And here's a listing of the MATLAB code. Fairly simple code. So anyway, this one here was a little bit different than the other ones in the fact that although we wrote the separable form of the solution, we got the characteristic equation through enforcing the boundary conditions. The characteristic equation we got was not one we could solve just by inspection. We have to resort to numerical means. That's more the rule rather than the exception. There are far fewer problems with closed form solutions than those for which we need to use MATLAB to solve.